Today we're going to introduce the concept of excenter for a triangle. So given a triangle ABC, let's look at the exterior angle bisector for angle B and angle C. The exterior bisector for angle B right here. This is the bisector, right? The exterior bisector for angle C, this one. So this is the bisector. So in theory, they're going to meet at a point, right? Let's call that IA. Now, AIA is going to be the interior bisector, which bisects angle BAC. So this one equal this one. All right, that's the so-called excenter, IA. So in theory, two exterior bisectors, one interior bisector, these three lines are concurrent. And the proof of that is quite straightforward. So basically from IA, you draw three vertical lines onto AB, onto BC, also onto AC. That because this is a bisector, these are 90 degrees, then this triangle is congruent to that. So you have this one equal this. All right, and then also you have this angle equal that, 90 degrees. So now you have this triangle congruent to this one. So you have this equal this. Now you have all these three segments equal, okay? But in particular, this now equal this, right? IAD equal IAF. The consequence of that is that this triangle now is congruent to this one. All right, let me clear the graph a little bit. What I mean is this triangle is now congruent to this one. Okay. Why? Because they're both 90 degrees. They share hypotenuse and they have one vertical leg the same. And by Pythagorean, the other vertical leg must also be the same, right? It's like SSS, right? Congruent. And because they're congruent, so this angle equals this angle. All right? Now, the importance of this excenter is not just, okay, three lines are concurrent, you know, what do we do? The importance is like the three lines, if two of them meet at that point, then the third one is free, right? It's like buy one, get the third one free. And I will show you what that means. All right, what I mean is, for example, all right, I have a, for example, okay, it's a 30, 60, 90 triangle, okay? This is 90 degree, A, B, C, this is 60 degree, okay? This is 30, okay? So I draw a line here such that this is 60 degree, okay? And I draw the angle bisector for ABC. So I draw a angle bisector right here that bisects the 90 degree, okay? So suppose it's gonna meet over there at point D, all right? So this is 45, 45, all right? Now I ask, if you connect AD, for example, okay, I connect AD. What's this angle? What is angle DAC? In case you're doing some angle chasing and stuff. Well, Now you have heard of excenter, all right? Is there excenter here somewhere? Well, excenter exists versus a triangle, right? There is a triangle ABC, then there is an excenter facing vertex A, right? All right, so what do you think right here? For example, D is the excenter for triangle ABC. Why? Because this is an exterior bisector. This is an interior bisector. So the third one must be an exterior bisector. So this must be 75. And that one is also 75 because it's going to be an exterior angle bisector. That makes sense? All right. Okay, so last time we also mentioned something about something related. Let's take another look at it. So triangle ABC, I draw the circumcenter, circumcircle, and I is the incenter. I extend AI, let it meet the circumcircle at point D. Right? We proved that this equal this equal this. Okay, now if IA is the excenter, then this is going to be a 90 degree. And that one is also going to be a 90 degree. And so then this also equals, right? These four segments, they are all equal. And so there is a circle with D as center, DI as radius, IA is a diameter, right? For this circle, you can draw the circle that passing through B, I, C, and IA, all right? And D at the center. And this is our excenter. All right, now there is another circle here. Let's not get confused. So this circle right here passes through B, I, C, and IA, all right? D is the center. Now there's another circle here, which is this one. Think about the graph that you've just seen previously. If you notice that this equal that, these three, and then if I draw a circle with this as center, I could have drawn a circle like that, no? Because these three segments are equal. So this circle is going to be like tangent to AD, tangent to BC, tangent to AF, right? That's called the X circle. Let me show you. It's this one. The graph is getting bigger. So I use IA as center, use this segment as a radius. Let's call that RA, all right? This radius is associated with this X circle facing vertex A. So the notation here has a capital A in there. All right, so in theory, a triangle ABC has three excenters, has three X circles. All right, the graph is getting bigger, but let's just focus on one today. All right, the one that's facing vertex A, exteriorly bisecting angle B and C. All right, so this circle right here is called the X circle, right? It's tangent to AB, AC, and BC. It's tangent to the three sides of the triangle, right? Very interesting, okay? Tangent to the three lines, but you know, like tangent to AB on the extension, tangent to AC on its extension, tangent on BC in the middle right here, right? Interesting. What kind of circle is tangent to all three sides of a triangle? We have seen one before. something called an ink circle with incenter as the center. You can draw like a circle like that, right? The inscribed circle, right? That circle is tangent to the three sides. Now I can draw a much bigger one, the X circle, which is also tangent to all three sides. Now that's interesting, no? Is there any relationship between this circle and this one? Probably there is. Also, what's the value of RA? Like we could calculate R. For example, by Heron's formula using areas. We could calculate R. Why? How do we do that? For example, this is C, this is B. If I tell you the three sides of a triangle A, how do we calculate R? S times R is the area. But in the meantime, this equals from the Heron's formula, right? Where S is defined as half of the perimeter. Okay? So, what about RA? If I tell you ABC, you think we can calculate that? Maybe. Right? That's something we're going to look at next time. All right, but I want you to start thinking about, well, so I'm going to provide you a little better graph, like this one. All right, it's getting really big. So I draw a very nice ink circle. I mark every contact point of the tangents. Now there are quite a couple of equal segments, all right? For example, for beginners, AD, I claim AD equal AF. Think about why. Why is that? I claim, for example, okay, I claim CE equals CF. And why is that? Think about it. Think about it, and we'll talk about next time, all right? X circle is quite interesting, and there's a lot of results coming out of it. And we're going to look at them in detail, one at a time, right? Don't want to overwhelm you, but it's quite a lot of results here. So think about this, all right? Think about these couple of days. Now, I want you to also try practice this problem, which is a very interesting problem. Competition problem in Moscow, 2001. A ball placed at point A inside an angle with vertex M. You struck the ball starts moving this way, touching the wall, bounce off this way. It's bouncing, so it's like a mirror, right? So like this angle equal this angle. Makes sense, no? It's kind of a reflection. Bounce off like the mirror, touching again on this wall, bouncing backwards, straight back to A. It returns back to A. That's very interesting. So this angle equal this angle. All right, so if that happens, prove the circumcenter of triangle BCM. Where is triangle BCM? Triangle BCM is this one. The circumcenter of this triangle, so basically this point, right? There's a circle here, lies on the line AM. Lies on the line AM. All right. I suppose that you should pause the video and work on this problem. And if you need an hour, that's normal. If you need a bit more time, that's okay. If you got stuck, go read a book and come back. There is nothing that you don't know in order to solve this problem. I have already showed you everything you need to know to solve this problem. All right, now, if you have tried enough time, I hope you solved it, and here's the solution. All right, if you extend AB, this angle equal this, no, opposite angle, but then equal this. It's because it's bouncing, right? Bouncing off the wall. So BM is a exterior bisector, bisecting the angle here. All right, it's the exterior bisector for angle ABC. All right, similarly right here, this is also a bisector. It's also exterior bisector. So right now, interestingly, we actually see that M is a excenter for triangle ABC. Triangle ABC, if you think about it, M is the excenter. If M is the excenter, then AM is the interior angle bisector. All right, so then this angle equals this. Now, where is my O, the so-called circumcenter for triangle BCM? What is that point? Think about it. Now you start to, once you realize M is the excenter, the problem is pretty much solved. Okay, why? Because as we know, the theorem tells, right, BCM's circle has diameter IM. I is the incenter for ABC. IM is the diameter. O is the midpoint of IM. O obviously lies on AM. AM is angle bisector. In the meantime, O is the intersection of AI versus the circumcircle of triangle ABC, the blue circle. Right, O is right here. It's on AM because M is the excenter, right? You remember the theorem? Right, IM, this line is the diameter for the circle of BCM. All right, O is the midpoint. And also O lies on the circle of ABC. All right, I hope you solved the problem. Now, if you're looking back, well, what's so hard about, I mean, if you didn't solve it, and now you see the solution, I think there's one thing that you start to realize: solving a difficult geometry problem is it's not just about, oh, whether I know the theorem or not. You might know a whole lot of theorems, but you may not be able to solve a problem. The difficulty is really see through the disguise. The problem comes in with the disguise, right? Where there was no mention of any angle bisector or any excenter whatsoever, right? It just says the ball is bouncing off. You know, there's some equal angles, but there wasn't any indication of any bisector or anything. So the critical step is to see through the configuration and recognize something hiding behind the disguise. All right, that's a skill that takes time to develop. All right. Okay, thank you, everyone. Hope you like what you're seeing. And then I should see you next time soon. And we should talk about the excenter and X circle radius and stuff like that. All right, see you soon.